Our first speaker, we have Bobby Pascua here. Bobby was undergrad at Berkeley and is just finishing up his graduate degree at McGill University, and he'll be telling us about, well, the research, I guess, from both of things, probably. Bobby, take it away.
Awesome. Thank you. So I guess I don't need to do my own introduction. So, here we're talking about some of my work with the HERA experiment. Now, HERA is a cosmology experiment, so I want to start by setting the stage and just a little bit of cosmology review. Many of you, or some of you may have seen this graphic before. It was an artist's rendition of the universe's history, with an emphasis on the first billion years of cosmic evolution. And I'm just going to step through this real quick. So, all the way on the left, we have a combination. This is when the CMB, cosmic microwave background, was produced. And in the context of doing 21 centimeter cosmology, this is our backlight. Okay, now following recombination, we have the cosmic dark ages. So we don't have any stars or galaxies yet. It's just matter collapsing under gravity. Until eventually things will collapse enough to kick off star formation and form galaxies during the cosmic dawn. Now the radiation from these first luminous sources would go on to heat and ionize the intergalactic medium throughout the Epoch of Reionization. And this process of heating, ionization, and gravitational collapse continues and continues and continues until eventually we get to the present day, where the IGM is basically entirely ionized, and we live in this universe of dark energy domination and an accelerating rate of expansion. Now the goal for 21 centimeter cosmology is fairly straightforward. We want to constrain cosmology and astrophysics over the cosmic timeline through the 21 centimeter signal from hydrogen. So remember back to quantum mechanics, there is a hyperfine transition of hydrogen, and that can either enhance or suppress the signal from the CMB through this interaction, and that is the physics that we leverage to do our science. Now we work with two different experiments that do this. First is HERA, which is targeting the 21 centimeter signal during cosmic dawn and reionization. At this time, neutral hydrogen is primarily in the intergalactic medium. And I also work with HERA, which provides a complementary view of the universe at low redshifts, when neutral hydrogen is primarily in galaxies. For the material I'm going to talk about today, I am mostly going to focus on what we've done with HERA. This is not a value statement of any sort, it's just like we've taken data for about 7 years with HERA, and we just installed our first antenna with Cord a little less than 2 weeks ago. So, neither of these experiments are going to make pretty pictures like this, but instead we are targeting a statistical detection of the 21 centimeter signal. In particular, we want to measure the power spectrum of fluctuations in the 21 centimeter signal. So, how much variance is there and how bright the 21 centimeter signal is as a function of physical scale. To orient you, large K modes correspond to small physical scales, small Ks corresponds to large physical scales, and we want to constrain this over cosmic time, right, various redshifts. Now, why do we care about the fluctuations? Well, here's what the universe may have looked like early on in reionization, and a little bit later, and a little bit later still. And hopefully this convinces you that the distribution of fluctuations in the 21 centimeter signal is sensitive to when we actually made the observation and the details of the astrophysics of reionization. So by constraining the power spectrum, in principle, we can learn about the first stars and galaxies, and we can also learn some of the details about how reionization unfolded. So these are the two big thrusts of the HERA experiment. These are our big science goals. Now, how does the experiment work? What is the experiment? So, hydrogen epoch of reionization, I hope the name is fairly straightforward. We're interested in reionization, and we are using 21 centimeter signal from hydrogen to study it. We are a fairly large collaboration. This is just a small group of us at our last in-person meeting. At the current stage, I think we have something like 15 to 20 member institutions across the world. And we've got about 80 active members. I don't know, that was about the length of the author list the last time I published a collaboration paper. Before I go on, I want to thank our amazing site crew, who you can see here. These are the people who built the telescope. They're the ones who, if something breaks on site, they're out there to fix it. We really would not be able to do the science that we want to do if not for them. So I'm immensely grateful for our site crew. Now back to the experiment. HERA is located in the Karoo Desert in South Africa. It is fairly remote. The nearest town is about an hour drive away on mostly dirt roads. If you zoom in on Google Maps, you can actually see the array from space. So you see we have this dense hexagonal core of antennas, and we actually have 2 rings of outrigger antennas. If you get a bit closer to the ground, you can start to see what individual antennas look like. And to give you a sense of scale, here's me working on one of the antennas on a redshifted site. So the feed is lower here, and I was just testing different ports, seeing if anything was busted. Each dish is 14 meters across, so that's like roughly the size of this room. And you can see the feed is about person height. And if I give you a side view, you can see we have the feed suspended something like 7 meters above the center of the dish. These are fairly large. And we have 320 of these in the core. So, when I talk about antennas going forward, what I mean is this combination of the dish, which focuses the radiation, and the feed, which converts it into an electrical signal. Now, fundamentally, HERA is an interferometer, and I assume most people don't think about interferometry, so there's a little crash course in interferometry. I'm going to pick a pair of antennas. I'll abstract this away a little bit. So I have the ground, I have my two antennas. They're separated by some baseline. There's electric fields coming in from the sky, and the antennas take that electric field, convert it into voltages, and then we cross-correlate those signals to obtain the visibility. You can think we're just taking the signal from one antenna, and we're interfering it with the signal from another antenna, and that's the data product we get out. So what we measure depends on which pair of antennas we chose. And assuming that we built all of our antennas to be the same, the visibility we measure is actually uniquely characterized by the separation between the antennas. In a little bit more detail, sorry, there's some math. The visibility I measure is a function of frequency and baseline. What it depends on is how each antenna sees the sky. This is called the primary beam. Basically, how sensitive is the antenna to radiation from a particular direction on the sky. I also care about what's on the sky, right? The distribution of flux on the sky. Generically, there's some diffuse stuff that has all sorts of strange structure, and there are a bunch of point sources on the sky. And then the thing that really characterizes the visibility is this fringe pattern. So this is telling me when I have electric fields coming in from a certain part of the sky, what is the phase that the interferometer measures it to have. The orientation of this fringe pattern is determined by the baseline orientation. So here I've chosen a baseline that is either pointing northeast or southwest, I don't know. If I were to rotate the baseline, the orientation of these fringes would change, and then the spacing of the fringes depends on the length of the baseline in units of wavelength. So you get a little bit of coupling to the frequency there. The basic idea here is if I have a longer baseline, that fringe spacing is shorter, and if I have a shorter baseline, the fringe spacing is larger. So what that means is short baselines are sensitive to large-scale fluctuations on the sky, long baselines are sensitive to small-scale fluctuations on the sky. So hopefully, for folks who like to think in Fourier space, that should motivate the idea that a baseline actually measures a Fourier mode of the sky mission. Right, so by taking a measurement with a particular baseline, I am probing a particular Fourier mode on the sky. Now with 21 centimeter, we are observing a very narrow spectral line feature. And thanks to cosmological redshift, what that means is that by making the observation at different frequencies, I'm actually measuring a signal from different positions along the line of sight away from me. So if I do another Fourier transform along the frequency axis, I'm secretly doing a Fourier transform along the spatial axis along the line of sight. So my delay transform visibilities are actually probes of individual Fourier modes of the 21 centimeter signal that we want to measure. So the idea here then is that using this sort of delay spectrum approach, I can build up the 21 centimeter power spectrum mode by mode, depending on how I've chosen to sample different frequencies and how I've chosen to arrange the antennas in my array. Now, whether this works or not is completely up to how well we can control systematic effects in the data. So now we get to air some dirty laundry. I'm going to talk a bit about mutual coupling. This is a very challenging thing that we've been dealing with lately, and I have a picture of the array here to help motivate it. So remember, the way an antenna works, radiation comes in, gets focused by a dish onto a feed. But all the feeds can see each other, and what's worse is they can actually see into the dishes of neighboring antennas. So by having each antenna in a sea of other antennas, it actually changes how the antennas see the sky, or said differently, there's some coupling between antennas. Now, to get a handle on how this coupling behaves, we came up with a simple physical model. So I have radiation coming from the sky, it's absorbed by an antenna, and then it gets re-radiated into neighboring antennas. And now what this does is it induces additional correlations in the data. So, said a little bit differently, there is excess structure in the visibilities that would not be there if not for the presence of other antennas in the array. Now what does this mean for the visibilities? So we'll use simulations to guide the way. Normally when I plot the visibility, I would have it as a function of time on the vertical and frequency on the horizontal, but I've decided to Fourier transform along both axes. So now I have what's called fringe rate on the vertical and delay on the horizontal. The main motivation for this is that different components of the signal separate nicely in this space, and this actually gives me a geometric view of the data in the sense that the majority of the features in the space can be explained by just appealing to the geometry of the array and the geometry of the signal in the sky. So the foregrounds, this is emission from our own galaxy and other galaxies between us and the clouds of hydrogen that we want to detect. They're confined to a finite range of fringe rates and a finite range of delays. The 21 centimeter signal we're after is confined to an even more narrow range of fringe rates, but a broad range of delays. If I isolate the mutual coupling signal from just this re-radiation mechanism, it's basically like I took the foregrounds and I smeared them out in this space, and the exact way in which I smeared them out depends on the geometry of the array. And if I add all these together, you can see that the foregrounds and the mutual coupling almost entirely swamp out the 21 centimeter signal. Now, this is all in simulation. Why should you trust any of it? Well, here's some data. I picked 4 different baselines. Again, looking at them in this fringe rate versus delay space. And if I look at simulations of those 4 baselines, we start to see similar features. So where I see X's in the data, I see X's in the simulations. Where I see slashes in the data, I see slashes in the simulations in the same direction. So if you take a close look, you'll see that the details don't all match up, but qualitatively we are producing many of the important features that we see in the data. So what we can do then is use our simulations as a guide for figuring out how we can even hope to remove the mutual coupling. So to make that a little more concrete, let's compare the 21 centimeter signal against the mutual coupling signal. And the simplest thing I can do is throw down a filter. So throw away everything in the grayed out region and keep everything else. And you see with this particular filter that I've chosen, I discard the majority of the coupling signal and I keep the majority of the 21 centimeter signal. A caveat though is that no matter what fringe rate filter I throw down, some of the mutual coupling signal is going to persist. So what does that mean for our power spectrum, right? That's the thing we want to characterize. How does mutual coupling affect the power spectrum? So here we're looking at power spectra in cylindrical Fourier space. I have Fourier modes along the line of sight on the vertical. You can think these are the different delays. And I have Fourier modes in the plane of the sky on the horizontal. These are measurements from different baselines. Okay. In this space, the foregrounds are confined to a wedge. The 21 centimeter signal occupies modes all across the space. The mutual coupling signal, you can think, I basically take the foregrounds, smear them out vertically and horizontally. So I take that wedge, I turn it into a brick. And then if I fringe rate filter before forming power spectra, you see that I do mitigate the coupling. I remove quite a bit of power from the coupled signal, but there are still residual coupling artifacts that are in excess of the 21 centimeter signal. So what that means is that fringe rate filters don't quite go far enough. And here are some spherically averaged power spectra. The solid line is the coupling signal. Dashed is what we get after we filtered. Dot dashed is if all we have to worry about is foregrounds, and the pink dotted is the 21 centimeter signal that we simulated. And this gray line is a little bit of an updated forecast of HERA sensitivity. So the main thing to keep an eye out for here is where does it transition? Where do these lines intersect each other? Because the basic idea is we avoid the foreground. So we'd want to go to the K modes that we think are not contaminated by foregrounds, but instead dominated by the 21 centimeter signal and do our science there. And what coupling does is it basically takes that foreground signal, throws it out to higher Ks, and it takes a lot more time to get the sensitivity to these Ks. So we need to figure out how to do better. We are working on it, but it's hard. Now I think I'm getting close to 15 minutes or so I'm just gonna quickly wrap up. So just the key ideas on mutual coupling. we see evidence of mutual coupling in the data that broadly agrees with our simulations. We can mitigate it by filtering it. I didn't have time to go over this, but we can actually analytically figure out how much of the 21 centimeter signal we throw away for any filtering filter we apply. This actually extends to like time averaging and all that too. Here's just a schematic showing how much signal loss we induce for every different baseline in the array and all the different redshifts that we make our measurements. And we need to do better. We're trying to do better, but it's hard. Progress is slow and hard-earned. It's not the happiest note, but I think I'll stop here for discussion.
Questions?
So is this why core has the receivers inside the dish?
Yes, this is the major motivation for Cord and putting the feeds so deep down in the dish.
If you go back to the pictures showing the feeds hanging over the dishes. Yeah, so the cord feed actually grew out of investigations of this feed. So it is a modified version.
It looks sort of similar, yes.
And for people who aren't familiar, sort of think of the dish continuing up to maybe here, and then shrinking the whole thing down to get to a shorter wavelength. So, yeah, the cord design is to completely blind them from each other. And is the verdict that that was a good idea? It costs a lot.
Well, I guess what preliminary simulations suggest it was a good idea. I have been handed some simulations of the beam to predict what the coupling, at least through this radiation model, would look like, but I have not yet had time to continue it. But at the very least, like, sort of direct radiation from one feed into another is suppressed by it when you put the feed deep down in the dish.
Yeah. Other, oh, sorry.
So is the mutual coupling only from the feeds seeing each other, or are there other ways of coupling?
Yeah, great question. There are definitely other ways. One of the things we've actually learned from EM simulations of this is that most of the coupling isn't actually the feed to feed, but rather, say, this feed seeing the far side of the dish with another feed. Basically, there are lots of different avenues for the signal from the sky to bounce from one antenna to another, and those will all manifest as mutual coupling. And the nice thing with the pre-radiative model is that the geometry is fairly similar, so the way these features manifest in the rendered versus away space is similar, even if the details don't quite match. But yeah, many other mechanisms.
Along those lines, I wanted to ask, when you're simulating these, how large is that parameter space that you're exploring, coupling adjacent feeds or two over or off the dish?
Yeah, so let me...
I know in Chime it's become sort of a nightmare, but the coupling between feeds, you have to include maybe 100 germs.
Yeah. So if we wanted to do like simulations of this, that's out the window, but those are way too expensive. But by modeling it as a re-radiation, so I can generate the data in this bottom left from, say, just the visibilities, and I need to know what is the beam on the horizon and what's the, say, reflection coefficient to do an impedance mismatch between the feed and the load that's attached to it.
Okay.
Yeah, so I literally just get to write down a gigantic matrix product. It mixes visibilities and time visibilities. Also numbers. You can compute this for the full HERA array. And I think order a second. So,
It's relatively cheap. If there are no other questions, I did have one very silly question. I'm not used to thinking in frame rate delay space.
yeah.
What are the two little dots on the 21 centimeter signal?
So this is actually a pitchfork, which people may or may not believe whether it's there for the 21 centimeter signal. You can think what the pitchfork is so for a baseline, if I look at the two directions along the orientation of the baseline, there are these regions of roughly constant phase along those directions, and so a interferometer can actually couple to the monopole through those coherent patches. And so if the 21 centimeter signal has a monopole in it, which for these simulations it did, then you get, yeah, those two dots. If you don't include a monopole in your 21 centimeter signal, then they will not show.
All right, if there are no other questions, thanks again, Bobby. Bobby's around today and tomorrow. I think probably has a little space left in the schedule. If people are interested in talking, chase him down.